from Mission Control Houston and the International Space Station Flight Control Room. At this hour, the 43-foot-long, 22.5-ton Nauka multi-purpose laboratory module is on course and headed for its final approach for its docking to the International Outpost's Russian segment 8 days after its launch from the Baikonur Cosmodrome in Kazakhstan. Nauka is scheduled to dock to the Earth-facing port of the Zvezda service module at 8:25 a.m. Central Time, 9:25 a.m. Eastern Time, completing a long journey to the station over the past 8 days, a long journey enabling Russian flight controllers to perform thorough checks of the new module's propulsion and navigation systems, as well as overseeing the undocking of the Pirs docking compartment this past Monday that cleared the docking port for Nauka's arrival. We'll talk about the chronology of the last week's events in just a moment. Meanwhile, here in Mission Control in Houston, the Orbit 2 team of flight controllers is on duty at this hour, led by Flight Director Greg Whitney. Whitney, who is the second from the right on your screen as you look at him talking to Flight Director Chloe Mehring, is presiding over this team. He is the lead NASA flight director for MLM operations, Mehring, one of the new flight directors selected by NASA. To their right is veteran astronaut Drew Morgan, who will be talking directly to the space station crew during the course of the day. The center of activity today is taking place across the ocean, however, at the Russian Mission Control Center in the town of Korolyov outside of Moscow, where Russian flight controllers, including a team of Nauka specialists, are monitoring the module's systems in the home stretch of its trip to the orbital outpost. The rendezvous so far is going by the book. A series of so-called impulse burns, small thruster firings on the laboratory module, have taken place over the course of the past hour to fine-tune Nauka's procession towards its docking port on the Earth-facing side of the Russian segment of the station. The module's core's automated rendezvous system has been activated and is communicating well with a comparable system on the Zvezda service module. Inside Zvezda, cosmonauts Oleg Novitsky and Pyotr Dubrov have activated the telerobotically operated rendezvous system, the Toru system, that they will be operating in the unlikely event there would be a problem with the core system. They would take over manual control of the flying of Nauka for its docking to the station. Otherwise, Nauka would automatically dock to the docking port on the Earth-facing side of the Russian segment. The International Space Station is currently flying 258 statute miles over the South Pacific, about to begin a southwest and northeasterly track that will carry it across the southern Atlantic and the west coast of Africa a short time from now. Just to bring you up to speed on some of the updated times for activities between now and the scheduled docking of Nauka 51 minutes from now, at 7:59 a.m. Central Time, 8:59 a.m. Eastern Time, the module will begin an automated fly-around of the International Space Station at a distance of about 405 meters, a 115-degree fly-around that will position Nauka directly underneath the docking port on the Earth-facing side of the Russian segment of the station. About 10 minutes later, they'll put the brakes on. This is an automatic sequence, computer controlled. The huge module will begin a brief period of station keeping to allow Russian flight controllers to monitor its alignment and all of its systems at a distance of about 203 meters from its docking port. Once the Russian flight control team is happy with what they see, the commands will be given to resume final approach. And again, docking is scheduled at the moment with an updated docking time of 8:25 a.m. Central, 9:25 a.m. Eastern Time. A few minutes thereafter, hooks will close to form a hard mate between Nauka and the International Space Station. Its long journey will be at an end. The cosmonauts on board the station, Novitsky and Dubrov, will spend the next several hours after docking conducting leak checks at the docking interface between the International Space Station and the newly arrived module before they open hatches to the spacecraft later today. Nyoka is going to serve a variety of purposes over the course of its lifetime at the International Space Station. It will provide, in certain circumstances, role control and attitude control of the station. It will enable a propellant transfer capability between Progress vehicles and both the Zvezda service module and the Zarya module's propulsion systems. It will serve as a docking port for Soyuz crewed vehicles and uncrewed Progress resupply vehicles. We will provide a docking capability for a new module called the Node module, named Prichal, that will arrive at the International Space Station later this year. And it will be equipped with a robotic arm, courtesy of the European Space Agency, the ERA, or European Robotic Arm, that will serve for both external payload activities as well as other maintenance activities on the Russian segment of the station. It will provide an additional crew quarters for sleeping capability for crew members on board the station, an additional toilet, and an additional electron oxygen generation system. And as we mentioned, it will serve as an airlock for future Russian spacewalks out of the International Space Station. In fact, the first pair of spacewalks to begin the outfitting of Nyoka are planned for early September, September 2nd and 8th, respectively, the first of what could be up to 11 excursions by Russian cosmonauts to outfit this new module over the course of the next several months.
Oleg? Yes?
Олег, можно выдавать команду?
That's my name.
Значит, на метке 9 километров, которая ниже. На странице 67, шаг 11.1.
At 9-kilometer range mark, you are go to send command per page 67. And the time has already been provided to you. We'd like you to send that command as specified at the time that it's specified for. Copy. I remember VRTS, RODF, display for a communication system. Copy.
Through a translator, Russian flight controllers, they're in Korolyov at the huge Russian Mission Control Center for space station operations, talking to Oleg Novitsky in the Zvezda service module. And again, he and Pyotr Dubrov are situated at a control panel. Basically, it's a control panel with a joystick that is called the Toru panel, the telerobotically operated rendezvous panel, that they would employ in the unlikely event a problem would occur with the Corps' automated rendezvous system. However, Corps was activated a short time ago and locked on to the comparable system on the Zvezda service module, basically bouncing range and rate of closure data between the two systems to update Nyoka's navigation systems as it closes in for its final approach. We're about 21 minutes away from the beginning of a fly-around by the new module of the International Space Station.
I have sent the command to activate VHF-2 duplex. Copy. And then we're going to select channel 3 on the comm panel.
The journey of the Nyoka multipurpose laboratory module began 8 days ago, back on July 21st, with its launch 30 minutes before sunset in the Central Asian Desert at the Baikonur Cosmodrome in Kazakhstan, atop a Proton M rocket. It was about a 10-minute journey from the launch pad to its preliminary orbit on the 3-stage Proton, which delivered Nyoka into a precise orbit to begin a stair-step approach with a series of engine firings over the course of the past week to match the altitude of the International Space Station and put it in a position for this final phase of the rendezvous prior to docking.
Copy that, Oleg.
And I'll keep this activity open until I actually make that transition in, or put those books into the MLM.
Mark, we see your crew note, and that all sounds great.
With Nyoka on its way this past Monday, the operation to clear the docking port began on the Russian segment of the station as the ISS Progress 77 cargo craft attached to the Piers docking compartment that had been a staple item on the International Space Station for the past 20 years undocked from that Earth-facing port, backed away from the International Space Station over the course of the next 3 hours, and then executed a 17.5-minute deorbit burn to send both the Progress and the Piers into a destructive entry over the Pacific Ocean. So that port is cleared. There was a robotic camera survey of the docking port to ensure that all the seals on that docking port that had housed Piers for the past 2 decades were clean, that there was no debris. And as a result, the Russian flight control team decided no further action in the form of a contingency spacewalk would be required to clean that docking port prior to the multipurpose laboratory module arriving for its expected docking coming up in about 43 minutes.
Oleg, you can check the overlay with the electronic crosshairs. Copy.
And now from an external camera on the Nyoka multipurpose laboratory module, a good view of the International Space Station. This coming through external cameras on the new laboratory. And you can see in the lower left-hand corner the distance that Nyoka is from the International Space Station, just under 10 kilometers, and the rate of closure at 5.8 meters per second. That rate of closure will slow to a glacial 1/10 of a meter per second right before contact and capture with the docking port on the Earth-facing side of the Zvezda service module. Here in Mission Control in Houston, Flight Director Greg Whitney is several minutes away from going around the room conducting a final poll of his flight controllers to get a go for docking. All of the space station systems are in excellent shape as the Expedition 65 crew, led by Japan Aerospace Exploration Agency astronaut Aki Hoshide, who is the commander of the International Space Station, are going about their other chores for the day, scientific experiments and maintenance work, while the 2 cosmonauts that are part of the Expedition 65 crew, Novitsky and Dubrov, are otherwise occupied watching the approach of Nyoka for its docking coming up in about 41 minutes. The multipurpose laboratory module has conducted burns today, rendezvous maneuvers to fine-tune its path to the International Space Station using both its main engine and thrusters. There will be several impulse burns as Nyoka closes in on the station over the course of the next half hour. Those will be employed by the small thrusters on the module. And again, after docking and the retraction of the docking probe on Nyoka to basically pull the docking interfaces tightly together, the initiation of the closing of hooks on both sides of the docking interface will take place. That will require about 9 minutes of operation to make sure the hooks are closed. Once a hard mate is achieved, Then Nowitzki and Dubrovov can begin the process of conducting leak checks on the station side of the docking interface before they open hatches to the brand new module later this morning. Tomorrow, the crew is expected to complete the reconfiguration of Nyoka's propulsion system and then begin the checkout of a number of its internal systems over the course of the next few weeks. And again, they are scheduled to conduct the first two spacewalks, Nowitzki and Dubrovov, on September 2nd and September 8th to begin the outfitting of the brand new module. The first of those spacewalks, Russian spacewalk number 49, as it will be known, is to reconfigure its power systems and to hook up Ethernet connections in the multipurpose laboratory module from the Zvezda service module and begin the deployment of its crew quarters. After the second of the spacewalks, there'll be a TV system activation, and the Core's Zvezda system, the automated rendezvous system, will be connected permanently to the multipurpose laboratory module through a series of antennas.
But you're not MCC. No, we are MCC. It's just that we are not authorized yet until the specialists say so. Copy.
Nyoka now just 8 kilometers away from the International Space Station, closing at a rate of just over 8 meters per second. The International Space Station in the field of view. And again, this is an external camera view, an engineering overlay camera view from the multipurpose laboratory module as it closes in for its final port of call at the International Space Station's Russian segment. While this activity is underway down at the Cape Canaveral Space Force Station in Florida, preparations are underway for tomorrow's scheduled launch of an Atlas V rocket to send the Boeing Starliner spacecraft on an unpiloted test flight, the orbital flight test number 2, to the International Space Station. Launch time tomorrow is scheduled at 2:53 p.m. Eastern Time, with NASA TV coverage scheduled to begin at 2 p.m. Eastern Time. Docking to the station to the forward port of the Harmony module of the International Space Station is expected on Saturday.
Station Moscow on base to ground 1. Oleg or Peter, please activate a recording of video streaming from MPEG 2. That's complete, Tatiana. Thank you, Peter. Moscow Station for Toro. Go ahead. Oleg, go ahead for Moscow. Did we already complete Impulse 4 burn or not yet? No, we have not. Impulse 4 burn has not happened yet. Copy.
Дальность 6150, скорость минус 10.
Range is 6,150 meters, and range rate is 10 meters per second. Copy.
This is Mission Control Houston as we watch Nyoka continuing to close in on the International Space Station, now almost 5.5 kilometers away from the complex. The crew on board the station involved in a potpourri of activities, most notably by the Russian cosmonauts who are carefully watching all of the data coming in on their control panels in the Zvezda service module, watching the range and rate of closure by the new laboratory module on the station. They are poised to take over manual control of the flying of Nyoka should that become necessary in the unlikely event the Corps' automated rendezvous system would encounter a problem.
Oleg on Space Ground 1, go ahead. The trajectory is different from predicted trajectory. That's what I sort of gathered. So we're still standing by for impulse 4 burn to occur. Range is 5 kilometers. Range rate is 10.5 meters per second. Copy.
Дальность 3,8, скорость минус
3.8 kilometer range. Range rate 10.73 meters per second. Copy, Oleg.
Пошел разворот на торможение, так что все нормально.
Oleg, we are performing retrograde maneuver, so we're going to get back on the right trajectory.
Ну, захват есть, поэтому все нормально.
We're still locked on with the course, so it should get much better, and we should get better alignment. Right, and right now the camera is blurred, so I can barely see any parameters. Copy. And also, Oleg, please prepare to start the timer as soon as the retrograde burn is complete. At the end of the retrograde maneuver, I will start the timer.
This is Mission Control Houston. Russian flight controllers sending commands to Nyoka for a retrograde burn, basically a brief braking maneuver to compensate for a slight perturbation in the approach angle that the module was making towards the International Space Station. It still has good telemetry and good lock-on through the Corps' automated rendezvous system at this point.
The timer has been started.
And that retrograde burn or braking maneuver is complete. The Russian flight control team believes this will improve the approach angle by the laboratory to the International Space Station.
Reverse maneuver is in progress. Copy.
And Nyoka is currently maneuvering now to the right orientation to resume its approach.
Guys, we completed the burn and we are back to our regularly scheduled trajectory, so no worries. Oleg, you can send the TOR activation command and start the TOR test. Copy. When you perform the test, please provide continuous commentary. TOR is on from the SFS display.
That call indicating that the telerobotically operated rendezvous system called the Toru system has been activated. It's not yet being used. The Corps' automated rendezvous system still in play to guide Nyoka to its final destination. And again, a slight perturbation in its trajectory toward the station was negated by a retrograde burn. The Russian flight controllers now believe that Nyoka is in the right orientation and the right trajectory for its approach for a fly around of the station.
Configuration command is on and the LEDs are on. VPS initial is set and rotational hand controller is in operational position. I'm ready to perform the RHC test. Copy. And we started another retrograde burn, and there was no response to any of the hand controller inputs. Copy. I'll extend down on further TOR testing until we're finished with this retrograde burn. Standing down. Oleg, we lost video, so your commentary will be very important. Okay. I'm standing by for thruster activation. DKS thrusters are on. Copy. Let us know meters per second later. 2.46 meters per second for Delta V, and reverse maneuver has started. Copy. That's what we expected.
This is Fish on 2 for MLM docking prep.
Go ahead, Aki.
Major, just want to report all USOS crew are in position for the MLM docking.
Okay, copy, Aki. Thanks for the heads up. They are currently in the middle of Impulse 5.
Oleg, we're not getting the image. Please report. Oh, well, nothing to report yet. Copy. I'm ready for the rotational hand controller test. Copy.
This is Mission Control Houston. In the Zvezda service module, cosmonauts Oleg Novitsky and Pyotr Dubrov are testing the Toru telerobotically operated rendezvous system. In the event they will need it, so far the Corps' automated rendezvous system continues to guide Nyoka towards its destination for docking to the International Space Station. Now that its course has been slightly tweaked and corrected to fine-tune its approach to the station, a series of thruster firings are underway.
To the right. Indicators are not illuminated. Copy. Counterclockwise, indicators are not illuminated. Copy. Clockwise, indicators are not illuminated. So in this last set of testing, the indicators were not illuminated. How copy? And now, do I have you go for translational hand controller testing, or we have to stand by some more? Oh, no, you go ahead. Up, the indicators on the edge are illuminated. Down, the indicators that are on both edges are both sides illuminated. In the middle, no. To the left, the middle indicators are not illuminated. To the right, the middle indicators are not illuminated. The side indicators are illuminated. Pulling towards me, the same. And pulling away from me, the indicators on the sides are not illuminated. The indicators...
Nyoka continuing to fire its engines and thrusters in small impulse burns, as they are called.
May I use AGC mode at this time because the image is very dark. Stand by, please. The station image is in the bottom of the screen, and we can see the solar arrays. Moscow, how do you read me? We read you. Oleg, stand by. Now 560 meters range, 560, and closing rate 2.1. So you may perform step 11.3, command test. Okay, copy 11.3, test and acquisition and execution of commands from the panel. And I activated Rabota and BPS initial, copy, and AGC mode on, copy. Command for AGC mode is not going through. Copy. And do you have the indicator mark in the top corner? No. Rabota Indicators are illuminated only on the sides. Do you have any messages, number 91? Alex, in 4.5 minutes we will have a ground site for MLM, and we will do another set for Toro. So did you say AGC mode command, did it go through? No, it did not. Copy. And I sent this command again, and we have a range 350 and 11.2. And the image is very dark.
This is Mission Control Houston. The multi-purpose laboratory module about to pass within range of Russian ground stations so that Russian flight controllers there in the Russian Mission Control Center outside of Moscow can evaluate the data from the spacecraft as it is under 1,000 meters away from the International Space Station.
And we have a range of 314 and closing rate 0.7. And please continue reporting, continue voicing it down, because we do not have any video image either right now. 290 for range and closing rate 0.7. And the image is very dark. Alex, let's continue. Please do not forget to report to us. Copy.
This is Mission Control Houston. Based on the range by the data that has been received and the rate of closure, Nyoka should be in its fly around of the International Space Station as we stand by for another attempt at a tour route test of the telerobotically operated rendezvous system by cosmonauts Oleg Novitsky and Pyotr Dubrov in the Zvezda service module.
Copy.
$248
for range now. Copy. Did you copy? And please look on the right side of the page. 623.3. I reported. Copy.
We're standing by for regaining video over Russian ground stations from Nyoka and any video from external cameras on the International Space Station.
35. Range 226, closing rate 0.27. Copy. And reserve 621.2. We are getting the video image now.
Video now of the International Space Station from Nyoka, 217 meters away.
Range 217, closing rate 0.15, and reserves 619.7.
We're standing by for another test of the Taurus system, just in case it would be needed.
Range 213, closing rate 0.11, and reserves 617.
The multipurpose laboratory module is in its fly around of the station.
So BPS initial now, please. And monitor the power. And now I'm proceeding with the translational hand controller test. Down. No indicators illuminated. To the left. Indicators not illuminated. Copy. To the right. Indicators not illuminated. Copy. Counterclockwise. Indicators not illuminated. Clockwise. Indicators not.
There's our first view of the multipurpose laboratory module from external cameras on the International Space Station.
Now proceeding to translational hand controller test. Copy. Up. Only the indicators on the sides are illuminated. Down. Indicators on the sides only are illuminated. To the left, the same. Neutral. Indicators illuminated. To the right. Only the neutral indicators are illuminated. Pulling towards me. Only indicators on the side. Pulling away from me. Only the indicators on the side. Test of the translational hand controller is complete. Let us go back to 11.3, step 11.3 again. Copy, in work.
We're still trying to, we think it's still trying to acquire.
BPS initial.
We'll keep working, keep looking.
Работа was already on. We did not turn it off.
We did have it, then it went.
And AGC mode, command.
Okay, copy. Thanks for the additional info.
And please deactivate the работа or function. Copy. And the AGC command did not go through. Copy that. Range 200. Rate 0.05. And we do not have a video image again, so please continue your reporting. Now roll and executing the roll, and I do not observe the solar arrays. Copy.
Station Houston on 2 for Aki.
And the station is going by vertically.
Assuming you were talking about SSC-12 there in the lab, would you mind checking SSC-13 and note 2, see if you see it?
Now to the left. Copy. And Alec? On the BPS panel, do you have Работа deactivated? Yes, and I did report that. The function or Работа is deactivated. Range 195.
External camera view, but it's looking at Earth and the other.
Rate 0.04. Reserve 568. Alec, please press that button again to deactivate the Работа or function switch. Repeat, please. Please press
This is Mission Control Houston at a distance of 190 meters away from the International Space Station. Nauka's docking mechanism has now been powered up, and reports from the Russian Mission Control Center indicate that it has now been commanded for final approach.
How copy? Okay, then turn it back on and then turn it off, the работа or function switch. And I do not deactivate the BPS исходный. Okay, now I activated the работа or function switch, and the indicators on the sides are illuminated. Copy. And now I turned it off, and indicators are not illuminated.
Range is 188. Range rate minus 0.01, and resources 561.3. Copy.
That MLM is station keeping, and everything's looking great.
Copy. Thanks.
This is Mission Control in Houston. Russian flight controllers say that they're go for final approach. The multi-purpose laboratory module, approximately 188 meters away, closing at a rate of about 1/10 of a meter per second.
Range is 188.
So far, everything continuing to go fairly close to the pre-planned rendezvous procedures. The MLM Nauka is locked in to the docking port on the Earth-facing side of the Russian segment of the station.
Final approach. Confirmed. DPS activation. Confirmed.
Here in the flight control room at Mission Control in Houston, Flight Director Greg Whitney has indicated that we are go for docking as MLM slowly inches its way towards its final destination at the International Space Station.
Minus 0.8. Copy. The docking node is 1 square below. Copy.
Station Houston on 2, we have pulled go, and MLM is on 5.
The image is really dark. I can just see the outlines of FGB. Range is 154. Range rate is minus 0.8. Copy. Docking node is in the center, and the target is to the left by 1 square. Copy. Range is 135. Range rate is minus 0.8, and resource is 544. We copy. Range is 121.
The multi-purpose laboratory module, just over 100 meters away from the station, its navigation system performing normally through the Core's automated rendezvous system, closing at a rate of about 0.6 of a meter per second.
BPS initial or исходная has been sent. Operation, all LEDs are illuminated, all 4 of them. Copy. And it did work. Copy. And look at the VKU screen in the right-hand corner.
The International Space Station and the multi-purpose laboratory module flying 260 miles over western Kazakhstan.
And range rate is minus 0.5. Let's see if the image improves.
For SSC video,
I'm trying.
unfortunately, we're not.
And
Coors has locked into the docking port that was occupied by the Piers docking compartment for the past 20 years until this past Monday, when the unpiloted Progress 77 cargo craft departed the station attached to piers. The two spacecraft then deorbited to plummet into the Pacific Ocean, opening up this port for the arrival of the brand new Nauka module.
Resource is 535. The target is in the center of the periscope. Copy.
Unfortunately, we don't have KU right now, so we're not able to point cameras.
Range is 70. Range rate is minus 0.32, and the resource is 533. Oleg, you can deactivate operation. Работа. Operation is off. And once you reach the 30-meter mark, range is minus 0.25, and the resource is 532. Read it back to me. Activate Работа at 30 meters again, and then you will be working for page 72. We copy. We will activate Работа operation again at the 30-meter mark.
We believe that we have a camera trained.
And we'll be working for page 72.
Exactly.
Range is 49.
We'll try to sweeten that up.
The resource is 530, and range rate is minus 0.18. And we copy. We'll be working for page 72. We copy all.
Behind it, but the torch is blocking it.
Range is 47. Range rate is minus 0.18, and 530 is the resource. The crosshairs are aligned, and the target is in the center of the...
Still moving towards its final destination on the Corps' automated rendezvous system. Now just about 40 meters separating Nauka from the International Space Station, closing at a rate of just over 1/10 of a meter per second.
The range is 45, range rate is minus 0.18.
The visiting vehicle officer here in Mission Control, Tom Erkenswick, reporting nominal performance from Nauka.
Copy. Range is 40. Range is minus 0.14. 528, 527 is the resource, and the crosshairs are aligned. We copy. Range is 36. Minus 0.14 is the range rate, and the target is 1 square to the left, 1 square down. Copy.
Closing in on 30 meters away from the station. Nauka's automated rendezvous system is adjusting its path for the final few meters prior to contact and capture.
Abort with plus X has been activated, just in case. And then, how do you copy? We copy. Range is 25. And looking at the ruler, the range rate is minus 0.1. The resource is 527, and we're almost 1 square to the top of the center of the target. We copy.
Multi-purpose laboratory module, 43 feet long, 22.5 tons of mass, flying over southern Russia,
Range.
27 meters away.
is 22 based on the ruler. The range rate is minus 0.1. The resource is 527, and the target is off by less than a square. Copy.
On the right of your screen is the Soyuz spacecraft that carried Oleg Novitsky, Pyotr Dubrov, and Mark Vande Hei to the International Space Station back in April as the newest component of the orbital outpost closes in for its contact and capture with the complex.
We copy. The target is in the center and the crosshairs are aligned. Copy. Everything's good, guys. We copy. We copy. That's everything's good. Oleg. We are at 31 around, like, so use floodlight just in case.
We see it on the camera, thanks.
We didn't copy, Vladimir Alexeyevich. We didn't copy your last range. We're entering the... We're losing light. Yura, are you seeing the image? Yes, we are. The target is
15 meters separating Nyoka from the station.
Range is about 10 meters. The target is a little bit going off to the side. Copy. Range is 0.09. Oleg. Let's switch to the Toro mode. Copy. We are sending PU-BPS initial. Stand by, Oleg.
And for the final few meters, Oleg Novitsky taking over manual control of the flying of Nyoka.
Initial command. Range is about 10 meters. Copy. Range rate is minus 0.08. The crosshairs are aligned. Range is 6 meters.
6 meters now. Novitsky flying the Nyoka multipurpose laboratory module in for its docking.
Range is 5 meters. The target is in the center, and the crosshairs are aligned, and the range rate is minus 0.08. We copy. Range is 4. And the misalignment is unintelligible. We copy.
Standing by for contact and capture.
We are losing the image. The range is 3 meters. Copy. Range rate is minus 0.1. The target is in the center. The crosshairs are aligned. Copy. Range is 0.1. We're standing by for contact. And once you get the contact and please deactivate. Once you confirm contact, please deactivate PU-BPS. Copy.
Contact and capture. Docking confirmed at 8:29 a.m. Central Time. Nyoka has been a long time coming, but has now pulled into port at the International Space Station.
Congratulations. That was not an easy docking. We have deactivated the manual control mode. Copy. Oleg? Retraction.
Docking occurring again at 8:29 a.m. Central Time, 9:29 a.m. Eastern Time, as the International Space Station and Nyoka flew 260 miles over the border between Mongolia and China.
We copy.
The next step will be the start of the retraction of the docking probe to bring the two docking interfaces between Nyoka and the Zvezda service module into a firm handshake with one another to initiate the closing of the hooks on both sides of the docking interface. And the docking probe is now retracting. Once again, 8 days after its launch from the Baikonur Cosmodrome in Kazakhstan, a new module has arrived at the International Space Station. The 22.5-ton Nyoka multipurpose laboratory module has reached its destination on the Earth-facing side of the Russian segment of the station. We're standing by for the completion of the retraction of the docking probe and the initiation of the closing of the hooks to form a hard mate. The docking probe has completed its retraction, and we now have hooks driving on both sides of the docking interface to form a hard mate. Once that is completed, over the next 3 hours or so, Oleg Novitsky and Pyotr Dubrov will conduct leak checks on the station side of the docking interface on the nadir or Earth-facing side of the Zvezda service module, prior to the opening of the hatch to Nyoka for the first time later this morning. To recap, the Nyoka multipurpose laboratory module docked to the International Space Station about 5 minutes ago at 8:29 a.m. Central Time, 9:29 a.m. Eastern Time, as it and the International Space Station flew over the border of Mongolia and China, completing an 8-day journey for Nyoka. Hooks are now driving to form a hard mate between the newly arrived module and the international outpost. Oleg Novitsky One of the two Russian cosmonauts, part of the Expedition 65 crew, took over manual flying of Nyoka to dampen out some perturbations in the alignment of the forward docking probe with the docking port on the Earth-facing side of Zvezda for the last few meters of travel, and did so expertly as Nyoka hit the mark and arrived right on the money at its docking port. Nyoka executed an automated rendezvous up to that point of about 5 meters or so away from the station, at which point Novitsky took over control of the flying of the module for the final few meters with the telerobotically operated rendezvous system and completed its journey for its docking. We now have received confirmation that hooks have been closed on both sides of the docking interface between Nyoka and the Zvezda service module, so we have a hard mate. Leak checks now to follow over the course of the next 3 hours. With the arrival of the Nyoka Multipurpose Laboratory Module at the International Space Station, the orbital outpost now has a mass of 973,687 pounds.
Go ahead, Moscow.
So the brand new module that will serve as a docking port for multiple vehicles, as well as an airlock and a laboratory for scientific research, has now been added to the International Space Station 8 days after its launch from the Baikonur Cosmodrome.
I am activating BPS initial. Copy, the command has been sent. Operation is on. Copy. I am sending the command to deactivate the manual control mode one more time. Copy. Pulse mode. Translational hand controller has not been deactivated. Has not been activated. Skip that. Copy. Control TV command. And then the image from MLM has disappeared. And then symbol, Mac, SSC monitors. I am deactivating send commands. command has been sent. Outermost LEDs are illuminated, and we are transitioning to the backup receiver. Copy. The floodlight is not illuminated. Copy. Operation. And then middle LEDs are illuminated. And yes, it is possible. It's okay. I sent PU-BPS initial command. Copy. Retreat plus X not illuminated. Breakaway enabled is not illuminated. We copy. Network is off. Power supply to hand controllers is off. Transmit is off. Copy. And I am deactivating the transmit from panel 1. Copy. Copy. And I'm switching to SM BRTK display. Copy. And then server is off. Command sent, and I confirm that it is off. We copy. SM BRTK STTS. That's the display that we're using. We copy. And I am sending the command to deactivate the VHF backup RCVR to off. We copy.
This is Mission Control Houston, here in the Flight Control Room. Flight Director Greg Whitney and his team of Orbit 2 flight controllers watching over the post-docking operations involving their Russian counterparts at the Russian Mission Control Center outside of Moscow.
And
Nyoka docked to the Earth-facing port of the Zvezda service module about 14 minutes ago at 8:29 a.m. Central Time, 9:29 a.m. Eastern Time, as the International Space Station and the Multipurpose Laboratory Module flew 258 statute miles over the border of Mongolia and China. A few minutes later, the docking probe on Nyoka retracted to pull the two docking interfaces flush against one another, enabling hooks on both sides of the docking interface to close to form a hard mate. With that having been completed, Oleg Novitsky and Pyotr Dubrov, the two cosmonauts who are part of the Expedition 65 crew on board the station, began to work the initial phase of powering down the telerobotically operated rendezvous system, the manual system that Novitsky took over control of to fly Nyoka in the final few meters of its approach for docking, so that it could have a precise alignment with the docking port. Up to that point, it had flown precisely for most of the rendezvous through the Corps' automated rendezvous system. Leak checks now will be performed over the next few hours by Novitsky and Dubrov. The propulsion system on the multipurpose laboratory module will be placed into a safe configuration later today and again tomorrow to wrap up work with the MLM. Its systems will be checked out over the course of the next few weeks as Novitsky and Dubrov prepare for the first pair of what could be up to 11 spacewalks over the next several months to begin outfitting Nyoka and preparing it for operational activities in the months and years ahead. The multipurpose laboratory module again will serve as a docking port for both piloted Soyuz and unpiloted Progress vehicles, soon to also receive a module called the Node module named Prichal, that will provide a multi-port docking area for approaching and arriving Russian vehicles. It also will carry the capability to serve as an airlock for Russian-based spacewalks, which are currently being conducted out of the ISS Module on the space-facing side of the Russian segment of the International Space Station. Naoka carries additional crew quarters, an additional toilet, another electron oxygen generation system, and will provide attitude control and role control capability for the International Space Station. So a brand new module has been added to the station. Its mass now over 973,000 pounds as it continues to orbit the Earth, approaching some 23 years of operation. With that, we'll wrap up our coverage for today. Naoka safely at the International Space Station following its 8 days of travel, following its launch from the Baikonur Cosmodrome in Kazakhstan back on July 21st. One programming note, next up, as work almost never ends at the International Space Station, will be tomorrow's scheduled launch of Boeing's Starliner spacecraft for the Commercial Crew Program on an unpiloted orbital flight test number 2, as it is called, a 24-hour rendezvous from the launch pad at the Cape Canaveral Space Force Station in Florida to the forward docking port of the Harmony module, with docking scheduled on Saturday, July 31st. Launch coverage tomorrow from the Kennedy Space Center and the Johnson Space Center begins at 2 p.m. Eastern Time for a launch at 2:53 p.m. Eastern Time tomorrow, Friday, July 30th. With that, we'll wrap up our coverage for today. Naoka, safely at the International Space Station. This is Mission Control, Houston.
How do people live in space? One major factor is making sure everything is just right, including the temperature. People have lived on board the International Space Station continuously for over 20 years, something that is made possible through its cooling system. Liquid ammonia in specialized pipes throughout station acts as a coolant to keep the temperature habitable for humans. Every so often, the pipes will spring a small leak, and the ammonia escapes outside the ISS. Occasional leaks are expected and typically pose no threat to astronauts, but they're inefficient, could become a bigger problem if left unattended, and can be a hassle for astronauts to manually locate the leaks via spacewalk.
The ISS program recognized very early on that ammonia leaks could be a big problem, and with the large radiators, that they would be something that happened, every couple of years. What they would do is basically monitor pressure in gas lines in various parts of the system, and using those measurements, they're able to isolate a leak to some segment of the overall system. But they don't have the capability without REL of pinpointing where the leak is.
QREL, the Robotic External Leak Locator, a toaster oven-sized tool that can detect ammonia leaks outside of station. REL can locate an ammonia leak in a fraction of the time required for a manual search. Deployed by station's robotic arm, REL uses two instruments and plays a game of hot and cold.
The REL, it's a tool that includes a mass spectrometer and a total pressure gauge. So a pressure gauge is pretty straightforward. It just tells you the local pressure where it's pointed, and pressure is equal to the number of molecules that are there. The mass spectrometer is a little bit more complex. It not only tells you how much gas is leaking out, but it also tells you what that gas is.
Using these instruments, REL is able to detect the gases in its surroundings and follows the trail of ammonia until it finds the highest concentration, thus revealing where the coolant system has sprung a leak. Following the success of the first REL tool, launched in 2015, a second was launched in 2019. The REL tools were initially stored inside of station, which meant a lengthy and precise procedure to get them from storage out of the GEM airlock, picked up by Dexter for leak locating, and finally returned to the airlock. That's where RITS comes in. The Robotic Tool Stowage, or RITS, acts like a garage or robot hotel. It is affixed to the outside of station and has two ports for each of the REL tools to reside while not in use.
The RITS was launched in December of 2019, so it's been up on space station almost a year now. It was just kept in storage. It launched up in a kind of a foam box, and it was brought inside the space station. And just in July, the astronauts unpacked it, and they installed the leak locator tools inside it, and they got it ready. And then there was an EVA, the spacewalk was performed to install it on the outside of space station.
RITS and REL are just another example of how robots and astronauts can work together to enable a sustained human presence in space. Robotic tools are easy to use, efficient, cost-effective, and safe.
One thing I want to note is that the robotic servicing is all done by controllers on the ground. So having the tools outside, we don't need to involve the astronauts on the space station at all. It kind of saves them time, one less thing they have to worry about.
While the REL units, stored cozily in RITS, are utilized to keep astronauts safe on station, our team continues to develop and build on this technology on the ground.
So one thing I'm excited about as far as the RITS technology is, and this has kind of been an evolution of tool stowage designs that we've built. So this is going to be very, very valuable anytime you're going to have robotic servicing, which is going to be increasingly more frequent for exploration in lunar orbit, and also if there's any outposts on the way to Mars, we're going to see increasing amount of robotic servicing, and the robots are going to need specialized tools and ways to secure them safely and keep them protected.
As you can imagine, the ability to characterize the type of gas present and the ability to locate leaks have applications beyond just space station. Anywhere there can be a human habitat, like the Moon or Mars, a leak locating tool will probably be a must. Additionally, robotically characterizing gases in places we've never been before can help us learn more about new environments, laying the groundwork for future exploration.
Always nice to add a new piece of capability to the space station, and there's always a capable group of folks behind it, but this one is particularly special. Dave Parker battling ALS. Wonderful to see the project that he's been involved with from the beginning. To see these lights illuminate. Congratulations, Dave. Congratulations, Team Dave. Team Dave.
The International Space Station has been providing us with groundbreaking science and discoveries for over 2 decades. When you think of humans as a spacefaring species, you may think of it as something limited to the future or science fiction. But in fact, for more than 20 years, humans have maintained a continuous presence in space via the space station. During that time, we have reaped the benefits of the research and science conducted on board. We have also managed to learn and develop engineering capabilities on the prime real estate outside.
Some of the really unique things we've been able to do on the ISS include things around robotics and autonomy, and especially with a new national capability, an initiative we have going on around on-orbit satellite servicing, assembly, and manufacturing. I would tell you that the ISS was really at the forefront of us starting this activity.
There is still so much left to learn and so much technology left to be tested in this incredibly unique place.
Really, the ISS as an orbiting lab provides the agency with the opportunity to test things in a microgravity environment. The main difference between terrestrial Earth testing and ISS is exactly that microgravity factor.
Using Station to practice capabilities and see how technologies will look and work in space is comparable to having a dress rehearsal before a big play. It provides us with the opportunity to learn, adapt, and tweak things as needed to drive down mission risk and increase the chance of success. This is especially important when you consider that many of these technologies and capabilities are things that have never been done before. Things like robotically refueling satellites in space that weren't designed to be refueled. NASA has big plans for sustainable exploration at the Moon, Mars, and beyond. First on the docket is Artemis, for which NASA plans to send the first woman and the next man to the Moon. In addition to testing technologies, Station also provides NASA with the blueprint for long-term human habitats in space. From learning about how human bodies adapt to a space environment in the long term, to discovering how to grow food and more, the orbiting lab provides invaluable lessons. As part of the Artemis program, Gateway will be an outpost orbiting the Moon, similar to the way Station orbits the Earth. Like Station, it will act as a destination for astronaut expeditions and science investigations. Unlike Station, it could serve as a port for deep space transportation, such as landers en route to the lunar surface or spacecraft embarking to destinations beyond the Moon. Gateway is a critical component of NASA's Artemis program and is possible thanks to strides made with Station.
So many technologies are required for us to sustain presence both lunar and then eventually when we go on to Mars. But with the Artemis program especially, and the lunar surface initiatives we're looking at now involve advanced power capabilities, advanced propulsion, advanced communications, trying to go to optical communications from radio frequency, entry, descent, and landing of large scale mass. And again, the robotics and autonomy, I'll keep going back to, those as well, but many different technological challenges, exist and are needed for us to be able to sustain those. What we're doing now will determine the future of what the agency's capabilities are.
The International Space Station offers endless possibilities in the future to continue to advance our identity as a spacefaring species. Did you know that if you were born after 2000, during your entire life there has been someone living in space? That's thanks to the International Space Station, which celebrated its 20th anniversary of continuous human habitation in 2020. You've probably heard a lot about the incredible science that happens on board the station, but the outside is actually prime real estate for all kinds of experiments and technology development too.
The International Space Station is a great platform to demonstrate servicing technology because it provides power, data, there's robotics in space.
With Tech on Deck, we'll be talking about some key experiments that have taken place outside in the harsh environment of space, which will help us advance human exploration.
Nexus is NASA's Exploration and In-Space Services Project Division at the Goddard Space Flight Center. The goal of the division is to usher in a new era of more sustainable, affordable, and resilient spaceflight, both near the Earth, around the Moon, and deep into the solar system. Many members of the Nexus team started off with the Hubble telescope servicing missions. We've taken that technology, applied that to robotic servicing.
From robotic refueling missions that will help spacecraft live longer and journey farther to autonomous navigation systems, NASA's Exploration and In-Space Services Division has taken advantage of the wonderful opportunity station offers to test new technologies. As we look to exploring our solar system and beyond, and establishing a sustained human presence in space beyond low Earth orbit, many of these technologies will play a key role.
We use the robots in Space Station to demonstrate the technologies needed to enable satellite servicing in the future. We've also used the robots on Space Station to do some of the more repetitive tasks or the dangerous tasks that astronauts shouldn't be doing, like going outside the space station to try to look for ammonia leaks. Robots are very good at moving fine, delicate positions, moving back and forth, doing those sorts of tasks that would be challenging for humans to do.
In order to live in space, astronauts will first need to reach their far-out destinations like Mars. This will require refueling and replenishment of oxygen supplies, things the robotic refueling missions worked to demonstrate on station. They will also need to be able to construct, maintain, and repair their habitats, as well as adapt to unforeseen circumstances.
Because we're in space and low Earth orbit, we have lighting conditions that are representative of objects in space, and so allows us to launch tools and modules into orbit, put them on the space station, and then use those robotic technologies and all the infrastructure that comes with the space station to mature those technologies in a way that's much, much less expensive than if we try to launch our own satellite and demonstrate those for the first time, not using the space station.
For these endeavors, Nexus's work with astronaut tools, satellite servicing, and on-orbit assembly and manufacturing will do the trick.
We develop the technologies that are needed to advance exploration in ways you can service satellites in the future, build satellites and build structures on orbit, refuel satellites on the way to other planets, repair those satellites much like we do on that side of space station. Both humans and robots are used to maintain habitats in space. We're developing technologies that can be used by NASA and others to make those a reality.
The International Space Station is the perfect testing ground for technologies that will be used to propel humans farther than we've ever gone before. The station is helping us build the necessary foundation to make it possible. Outside of the International Space Station, space can be a lonely place. Most satellites are designed to live their lives alone, and we've yet to find life outside of Earth. This means that when we launch a spacecraft or satellite, for the most part it's on its own, and has a limited lifespan based on when critical items like fuel run out, or something breaks. You wouldn't throw away your car if it ran out of gas, and thanks to the advent of modern-day robotics, software, and computing power, we will soon be able to apply that logic to satellites. We are on the cusp of breaking the one-and-done paradigm that exists for most satellites. An important step in that direction is NASA's Robotic Refueling Mission, or RRM, demonstration on the International Space Station. Because refueling a satellite that was not designed to be refueled has never been done before, practice is key. With that in mind, the first two phases of RRM took place on station from 2011 to 2017, and tested the tools, technologies, and techniques to refuel and repair satellites in orbit.
RM and RM Phase 2 were designed to demonstrate end-to-end refueling of a spacecraft, as well as the first steps of cryogenic refueling or replenishment. We wanted to use the robot on the International Space Station to be able to demonstrate the technologies and techniques to do this refueling So we built innovative tools to bridge the gap between the robot and the payload interfaces.
Consisting of a module or box affixed to the outside of station and robotic tools, the demonstrations use station's Dexter robot to operate tools and test servicing tasks such as cutting and peeling back protective thermal blankets, unscrewing caps, turning valves, transferring fluid, inspection, and intermediary steps leading up to refueling.
Once we were all done, we were able to transfer fuel end-to-end through a spacecraft fill and drain valve that wasn't designed to be robotically refueled.
The RRM demonstration helped test and prove technologies that will make refueling satellites not designed to be refueled possible, something that will be further demonstrated by NASA's On-Orbit Servicing, Assembly, and Manufacturing 1 mission. But it also helped to lay the groundwork for designing future satellites in a way to make them more easily serviceable.
These missions were important because we needed to demonstrate in orbit that this technology was ready. There were a lot of people that felt that at the time of RRM that the technology was so far in the future that they didn't feel what we were talking about was possible. So we needed to demonstrate in orbit this technology so that we could start changing the paradigm and incorporate these technologies into the future spacecraft designs and missions.
RRM Phase 1 and 2 were all about preparing an interface for refueling, which in many ways is half the battle. To robotically refuel a satellite, you need to perform a series of highly dexterous tasks to even access the valve. The next step is to actually perform refueling tasks, which is what the next phase, RRM-3, has been demonstrating on station over a series of operations since 2018. RRM is a critical piece of the sustainable spaceflight puzzle that helps us with the ability to robotically refuel, repair, and maintain satellites in both near and distant orbits, well beyond the reach of where humans can go today. For generations, Mars has beckoned. Now, the red planet is within our reach. But how do we get there? The key is in the details, and in the technology. First and foremost, you need fuel. This is not only true for getting to Mars, but for any form of deep space exploration. Being able to replenish fuel on a long-duration journey means massive amounts aren't needed up front, freeing up space for other important things. Enter Robotic Refueling Mission 3, or RRM-3 for short. This demonstration launched to the International Space Station in December of 2018 and has helped us develop tools and techniques needed to replenish cryogenic fluid in space. Transferring cryogenic fluids has never been done before in space. These super cold fluids can be used as propellants, coolants, or for life support systems. Being able to replenish these fluids that run out, otherwise known as consumables, is an important part of the sustainable exploration roadmap. Not just for Mars, but for NASA's Artemis program, which will land the first woman and the next man on the moon. Since refueling cryogenic fluids in space has never been done before, RRM-3 tested the technologies and techniques needed to make that possible. First, we sent the RRM-3 payload and its 3 main tools to space station, where astronauts assembled the parts.
When I was living aboard the International Space Station in the spring of 2019, I was fortunate enough to take part in the very small part in the Robotic Refueling Mission 3. And my job was to unload the components of the actual RRM-3 from one of our visiting vehicles, and we take it into our Japanese experimental module, the GEM, where we have an airlock. And right inside of the airlock, we unpacked all of the boxes, much like you would a piece of furniture that you had to assemble yourself at home. So unpacked all of the pieces, we did a checkout, we worked with the ground, we got everything assembled, and then we placed it into the Japanese airlock. And from there, we were able to put it outside of the International Space Station. So my involvement in RRM-3 was the physical final assembly of the actual components.
RRM-3 was delivered to the space station by a SpaceX Dragon on the company's 16th Commercial Resupply Services mission and installed on the outside of station by the Canadian robot Dexter. Dexter then picked up the tools from the JEM airlock and installed them onto the RRM-3 payload. The ground operations team was now ready to begin operating the 3 tools to test how they would work in space. For the first set of operations, conducted in August 2019, Dexter used one of the RRM-3 tools to prepare the RRM-3 module's interface for transferring cryogenic fuel. The second set of operations was then conducted in October 2020. For these, Dexter used one of the remaining 2 tools to insert an 11-foot-long hose in an open port and the other snake-like camera inspection tools simultaneously to verify the hose's position in the inside of RRM-3's tubing. This marked the first time that Dexter had tools in both arms working the same tasks simultaneously. The RRM-3 demonstration added experience and information to NASA's knowledge base on the storage and transferring cryogenic fluids in space. It is currently still on station, where it will conduct one final set of operations in mid-2022. For getting to the Moon, Mars, and beyond, cryogenic fluids will be used as propellants and to maintain life support systems for astronauts. The Mars atmosphere is made up of carbon dioxide, which could be converted to liquid oxygen, a type of cryogenic fluid that could be used both as propellant and for breathing. Astronauts may be able to fuel rockets or replenish their oxygen supplies using compounds found in the Martian atmosphere. A tool on the Mars Perseverance rover called Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, is set to demonstrate the first ever conversion of Martian carbon dioxide to oxygen, which is another important piece of the puzzle. In order to make a sustained human presence in space a reality, humans and robots will have to work together using technologies like those developed by RRM-3 and MOXIE.
A lot of people ask about, whose job is exploring outer space? Is it robots or is it humans? And I believe that it requires teamwork between robots and humans, and that our exploration is not complete or even possible without both. So robots can go farther, they're less expensive, and they can go for longer periods of time. They don't require as much maintenance. You don't have to feed and care for a robot, much like you do if you send me back to space. So like the Mars rovers, the Galileo that explored Jupiter and its moons, the Hubble and the soon-to-be James Webb Space Telescope, they're doing missions in locations that humans, to this point, don't have the capability to go. There's also something very important about humans wanting to know what it's like to be there. It's not enough for humans to take a picture of Mount Everest or Antarctica and say, oh, okay, that's what it looks like. The human condition is we are born to explore. We're born to say, what if? What's just beyond what we know? And what is it like to be there? And so the human side of space exploration, first of all, it's orders of magnitude closer to Earth. We have not been able to send humans nearly as far as we've been able to send robotic probes. But they're 2 very different missions, and they serve a different type of curiosity.
Mars and deep space are calling human explorers, and RRM-3 is a step toward helping NASA answer that call. Though it sounds complex, the idea is simple. Having the ability to refuel will allow NASA to embark on longer journeys to explore the depths of our solar system. Did you know there's a 3-eyed raven currently perched on the International Space Station? Not an actual bird, but rather a technology payload that is helping NASA develop a relative navigation system, or autopilot, for spacecraft. Launched to station in 2017 aboard a SpaceX Dragon on the company's 10th commercial resupply services mission for NASA, and installed on the outside of ISS by station's Dexter robot, Raven is equipped with 3 distinct camera vision systems: visible, infrared, and LiDAR. Combined with NASA-developed software algorithms, this rotating module of technology keeps a weather eye on arriving spacecraft. Raven's head, containing its 3 eyes, or cameras, is always on the swivel, which is made possible by its integral gimbal.
Raven is an on-orbit test bed that was built to mature technologies related to relative navigation sensors and algorithms. Raven was launched to the International Space Station aboard a SpaceX Dragon capsule in February 2017. And it's been operational on the space station since that time. So using 3 different sensors on Raven that are on a movable gimbal platform, Raven can track the incoming visiting vehicle to station all the way from very, very far away, all the way up to where they dock with the space station. So basically, at any given time, Raven can tell you where the incoming visiting vehicle is in space relative to the space station and what attitude or pointing direction it is.
Raven sends the data it collects from tracking and observing incoming spacecraft to its processor or brain, called SpaceCube. This information then tells Raven how it needs to move to continue to track the spacecraft and gauge relative distance and positioning. NASA engineers have taken what they've learned from multiple Raven observations over the years to adjust and fine-tune the relative navigation system as needed, so it's ready for the upcoming on-orbit servicing, assembly, and manufacturing 1 mission, which will robotically refuel a satellite, among other things.
Raven is a sensor system that can image an object, process those images on board in real time with advanced algorithms, and calculate the pose of the object relative to itself.
These factors come together to create something like spacecraft autopilot. Much like a self-driving car can maintain cruise control based on the speed of the vehicle it follows, 2 free-flying spacecraft will be able to dock with one another using this technology. Though this operation is similar to the autonomous docking of visiting spacecraft to station, Raven's unique application is necessary for docking 2 satellites with the challenges of each moving and rotating in every direction during the rendezvous and docking phase.
Using that information to then guide the first spacecraft to autonomously rendezvous with and dock with the second spacecraft. So that means finding it in space, aligning with it appropriately, and then bringing the 2 vehicles together without smashing them into and destroying each of them, all without human intervention.
This capability is the kind of thing you need for docking with spacecraft that were not originally designed to be docked with and serviced, which happens to be a vast majority of them. That's why Raven's time on station is critical for the future of on-orbit servicing, assembly, and manufacturing, or OSAM. The OSAM-1 mission will use Raven's relative navigation capability to autonomously, meaning no humans involved, rendezvous and dock with the satellite, and then telerobotically refuel it. This will be the first time in history a spacecraft not originally designed to be serviced will be refueled as a means to extend its operational life. Raven is also important for future exploration missions.
Raven's technologies can be applied to future NASA missions because if humans want to make a footprint in the solar system beyond low Earth orbit, which is where the International Space Station is located, we're going to have to rely on some form of autonomous docking technologies in the future. Whether it be an unmanned cargo vehicle meeting up in orbit around the moon, refueling tankers located in geosynchronous Earth orbit, or a return vehicle arriving on Mars in advance of a crewed landing, all of these feats will require the technology we're developing with Raven.
Using its 3 eyes, Raven is looking to the moon, Mars, and beyond.
Relying on highly robust autonomous systems becomes more crucial the further you move away from Earth as the communications time increases drastically. Once you move past low Earth orbit, it becomes very impossible for humans on Earth to do these highly complex maneuvers in real time. It's more efficient to allow computers to perform these sequences autonomously without human intervention.
Although Raven has successfully concluded its main mission objectives, it remains on station. Meanwhile, its team on the ground is using what they've learned to develop more never-before-seen technologies that will enable future space exploration.
Before I started digging in that other bag, here you go. No problem.
If you need to fix something in space that wasn't designed to be fixed, it's going to take all the experience you can get. With that in mind, when the International Space Station's Alpha Magnetic Spectrometer, or AMS, needed repairs, NASA's Johnson Space Center and Goddard Space Flight Center used their joint expertise to make it happen. At Goddard, that expertise resides in NASA's Exploration and In-Space Services Division, or NEXUS, which evolved from the office that was responsible for the Hubble Space Telescope servicing missions. Key to these missions was the development of specialized tools. While you've probably heard of Hubble, you may not be as familiar with AMS, so let's start there. Designed for a 3-year mission of sifting through cosmic ray particles, AMS has been looking for signs of dark matter from its position on station since 2011. Hundreds of researchers have used the data collected to investigate the source of the mysterious substance to help us better understand the origins of the universe. To continue this important data collection, AMS needed an upgrade due to general wear and tear from the harsh environment of space, specifically a new cooling system. A repair could extend its life beyond what was originally planned. Sounds easy enough, right? In fact, due to the instrument's complexity and the fact that it was not designed to be repaired, even gaining access to the system to replace it was difficult. AMS's design did not incorporate the kinds of interfaces that make spacewalks easier, or have the ability to be serviced with traditional multi-purpose tools. And so, over the course of 4 years, NASA got to work designing and developing some of the most complex spacewalks since the Hubble servicing missions in the 90s and early 2000s to fix AMS.
The AMS tools themselves were unique. They were built specifically for this task, a task that was never intended to be performed on a spacewalk. And so that required a lot of thinking about how we were going to get inside so that we could access the tubes that we needed to cut into and then install the new thermal control system, but also how to put handling aids on it so that we had a place to attach our tethers, to attach our foot restraints, to have handholds, have a place to attach equipment that we needed out there.
NASA developed 20 specialized tools to make the job possible, and on November 15, 2019, astronauts Andrew Morgan and Luca Parmitano got to work. On this first spacewalk, astronauts needed to get access. By design, 5 of the tools could be seen floating off into space, attached to the debris shield that was removed to give the astronauts access to the heart of AMS.
The debris shield handling aid was one of the first tools that Luca installed on the EVA, and this gave us a handhold to install on the debris shield to work from, but also a handle for me to hold on to ultimately when we jettisoned it overboard to the aft side of the ISS, which was a lot of fun to do.
The astronauts continued with 3 more spacewalks over the next 2 months, using all of the specially designed tools. One such tool was the Tube Cutting Guide, which was a direct result of multiple practice sessions at Johnson Space Center facilities like the Neutral Buoyancy Lab. While practicing, astronauts communicated the need for a way to identify and verify the correct tubes to cut, since they all look the same to the astronauts' eyes within the spacesuit.
After we had removed the debris shield and the VSB cover, now we have the tubes exposed, and we actually had to cut into those tubes in order to pull out the correct ones to connect with the new thermal control system, the new pump. In order to do that, we had to be very sure of the tubes that we were cutting. These ingenious tube cutting guides installed over the top of the tubes and made sure that we knew and we were communicating correctly with the ground team to make sure that we were cutting the correct tube at the right time.
In January 2020, Luca Parmitano and Drew Morgan completed the 4th and final spacewalk to repair AMS. Because of their work and the ingenuity of tool designers and engineers, the instrument is now back in commission and able to continue to collect data about the origins of our universe for years to come.
People from Goddard and JC spent a lot of time developing these tools with their knowledge and the support of astronauts like Chris Cassidy. And we are very thankful that we were privileged to use those tools and to put them to very successful use. Thank you very much.